Every day, millions of people descend beneath city streets and board trains that travel through tunnels surrounded by wet soil, underground rivers, leaking pipes, and groundwater. Some subway tunnels even pass directly beneath rivers and harbors. And yet, most of the time, the tracks are not underwater. The lights remain on, the signals continue working, and trains move through the darkness as though the enormous weight of water outside the tunnel simply does not exist. So how do subway tunnels stay dry? The surprising answer is, they don't. Water enters underground railway systems every single day. In New York City alone, crews normally remove around 14 million gallons of water from the subway system every day. That is enough to fill more than 20 Olympic-sized swimming pools every week. The real engineering achievement is not creating a perfectly dry tunnel. It is controlling the water, collecting it, directing it, storing it, and pumping it away before it can reach the electrical equipment, signals, and trains. And when even one part of that hidden system becomes blocked or overwhelmed, an ordinary rainstorm can turn a subway station into an underground river. Today, we are going beneath the tracks to explore the drainage systems, pumps, waterproof barriers, flood doors, and emergency equipment that quietly keep modern subway tunnels operating. Welcome to Hidden Engineering. Part 1. The Underground Water Problem. To understand how tunnels remain operational, we first need to understand where the water comes from. The most obvious source is rain. A subway station may be underground, but it is connected to the surface through stairways, elevator shafts, ventilation openings, utility passages, emergency exits, and sidewalk grates. During normal rainfall, most water flows into street drains and enters the city sewer system. But when rain falls faster than the sewer system can carry it away, water begins collecting on the street. At that point, every subway entrance can become a funnel. Water flows down staircases, through ventilation grates, around elevator doors, and into the station. Once it reaches track level, gravity carries it toward the lowest sections of the railway. But rain is only part of the problem. Subway tunnels are built below the natural water table in many cities. This means the surrounding soil or rock may already contain water under pressure. That water searches constantly for a path into the tunnel. It may enter through microscopic cracks in concrete, construction joints, bolt openings, aging seals, or connections between different tunnel sections. Modern tunnels are built to limit this intrusion, often using waterproof membranes and compressed gaskets between concrete segments. But no underground structure remains perfectly sealed forever. Even a small amount of seepage becomes important when it continues 24 hours a day, year after year. Crossrail engineering documents describe how water can enter through joints in segmental tunnel linings and collect beneath the track structure if it is not given a controlled drainage path. Water can also enter from broken water mains, leaking sewer pipes, fire suppression systems, station cleaning, condensation, or utility failures. So engineers begin with an important assumption. Water will eventually get inside. The tunnel must therefore be designed not only to resist water, but also to manage the water that resistance cannot stop. Part 2. The first defense: keeping water out. The first layer of protection is the tunnel structure itself. In many modern subway systems, tunnels are built using large tunnel boring machines. As the machine cuts through the ground, it installs curved concrete segments behind it. Several segments form a complete ring, and thousands of rings form the finished tunnel. The joints between these segments are critical. Each joint may contain a flexible gasket. When the segments are bolted together, the gasket is compressed, forming a watertight seal. Some gaskets are hydrophilic, meaning they expand when exposed to moisture. This allows them to fill small gaps through which water might otherwise pass. Engineers may also inject grout into the space between the tunnel lining and the surrounding ground. The grout stabilizes the soil and reduces the pathways through which groundwater can move. In other tunnel designs, engineers construct a primary structural lining, install a waterproof membrane, and then add a secondary concrete lining inside it. The result is similar to placing a protective raincoat between two layers of concrete. But the weakest points are often not the middle of the tunnel walls. They are the connections. Places where one tunnel meets another, where a station joins a running tunnel, where cables, pipes, ventilation ducts, or emergency passages penetrate the concrete. Every opening creates another potential route for water. That is why these areas receive special seals, drainage layers, water stops, and inspection access. But preventing groundwater seepage is only half the challenge. Engineers must also stop large volumes of surface water from entering through station openings. After major floods, subway systems have increasingly installed raised entrances, higher ventilation structures, temporary vent covers, flood barriers, and mechanical closure devices. A raised subway entrance may look like an architectural detail, but those few extra inches can prevent street water from immediately cascading down the stairs. In areas exposed to coastal storm surge, protection becomes much more dramatic. Large marine doors can seal tunnel portals and ventilation openings. Other locations use deployable barriers or heavy covers that crews install before a major storm. Following Superstorm Sandy, New York's transit system invested in marine doors, ventilation closure devices, raised entrances, and other defenses intended to keep coastal flooding out of vulnerable underground infrastructure. These systems do not make the entire subway waterproof. Instead, they reduce the amount of water entering during the most dangerous period. Because every gallon stopped at the surface is one less gallon the pumps must remove below. Art 3. Using gravity underground. Once water gets inside, gravity becomes part of the drainage system. A subway tunnel may appear level when viewed from a train, but it usually contains slight changes in elevation. The trackbed, drainage channels, and connecting pipes are shaped so that water moves toward designated low points. Along the tunnel, water enters small grates, channels, or troughs. These may be located between the tracks, beside the rails, or beneath the track structure. The Federal Transit Administration describes tunnel drainage systems as combinations of grates, scuppers, pipes, drainage troughs, sump pits, and pumps. A scupper is simply an opening that allows water to leave one surface and enter a drainage pipe or channel. The principle is not very different from the drain in a shower. The difference is scale and consequence. A clogged shower drain is inconvenient. A clogged subway drain can allow water to reach switches, communication cables, signal equipment, and the electrified third rail. The drainage channels lead water toward sumps. A sump is a collection pit constructed at a low point in the system. As the sump fills, sensors detect the rising water level. When the water reaches a programmed point, the pump starts. The pump pulls water from the sump and sends it through discharge pipes toward a sewer, holding tank, or another drainage location. When the water level drops, the pump switches off. This process can repeat thousands of times without passengers ever knowing it is happening. Some systems use several water level settings. The first level starts the normal pump. A higher level may activate additional pumping capacity. A still higher level may trigger an alarm in a control center, warning employees that water is entering faster than expected. The sump also provides temporary storage. That storage matters because water does not always arrive at a steady rate. Modern resilience plans include increasing both pump capacity and sump pit detention capacity. A larger sump can temporarily hold more stormwater, instead of immediately sending all of it into an already overloaded city sewer.
So, how do subway tunnels stay dry?
They don't stay completely dry. Instead, they're designed to live with water. Tunnel linings and waterproof seals slow it down. Raised entrances and flood barriers keep large volumes outside. Sloped surfaces and drainage channels guide the water away from critical equipment. Sump pits collect it. Sensors detect it. Pumps remove it. Check valves prevent it from returning. Backup generators keep the system operating when normal power fails. And maintenance crews make sure that a piece of trash or a layer of sediment does not disable the entire chain. The next time you stand on a subway platform and hear water dripping somewhere in the darkness, remember, that sound does not necessarily mean the system is failing. It may mean the system is working exactly as intended. The real danger is not that water enters the tunnel. The danger begins when the water can no longer escape. This is the hidden engineering beneath your city. Thank you for watching. If you enjoyed this video, subscribe for more stories about the systems, machines, and engineering decisions that keep the modern world running.